So welcome everyone. This is Barb Tyson, and we've got another great Salty Dog webinar today. First off, we'd like to thank Hylas Yachts for their webinar sponsorship. It's because of this sponsorship by Hylas that we've been able to keep our webinar fees low. And of course, we'd also like to thank today's presenter, Simon Ytterbom, for sharing his time and expertise with us. Simon is with Victron Energy. Before we get started, please remember just to keep muted and to keep your video off. That keeps the webinar running smoothly. I have opened a chat box. You should be able to see that. And this is where you can type any questions or comments you have for Simon. Simon's going to hold his questions for a Q&A session at the end, but it's always a good idea to type your questions in as you think of them so you don't forget. We are recording today's webinar, and I will send a link out as soon as we have it uploaded. So let's go ahead and get started. Today's webinar is Offshore Power Management and System Design. And Simon, it's all yours.
Well, thank you so much, Barb. And yeah, let's get this presentation on the road. Thank you so much for allowing the opportunity to speak here. In this presentation here, we're going to cover a couple of different topics. The one that we're going to cover the most is the design aspect of a system, whether we are looking to increase our system, add more power to it, or if we're doing a whole overdo on a system. And we're going to cover some of the most common questions and concerns when we're doing so. We're going to look at some of the calculations to how we can achieve what we're looking for in our system. And we're going to touch on equipments, IP ratings, so on and so forth, some wiring, and the installation of it as well. So this is a pretty long PowerPoint, so I'm going to try to move forward at a pretty good rate. So it's good that we can access this recording afterwards. Would there be anything here? And then we'll cover some questions afterwards if I'm missing something. Okay, so the first thing that I'd always encourage anyone who's having a power system will help you read your charge and so on with your system. So if you are using just a voltmeter amp meter, for example, I would strongly recommend that the first thing you would do to your system is invest in a quality battery monitor that can translate what volts and amps into state of charge for your specific battery bank. For example, if you're just using a voltmeter and the volt will fluctuate depending on the load that you have on the battery. A starting battery in a car, for example, we know the battery is fully charged. We've been driving for a while, but when we're going out to start the engine, we know the battery voltage will drop down to, let's say, 10 volts. We know that the battery is still fully charged, even if it's showing a low voltage for that short period of time. So voltage is only a measure of the load put on a certain size of a battery. So that's why a quality battery monitor is important to have, so you can truly see what's going on with your battery and when you need to recharge and when you can use power because it's fully charged and so on. Just a little quick on how batteries are connected to when we're installing them in a system. If you need 12 volts, simply if you use one battery, we connect the positive and negative to our loads. If we want to increase the voltage for our system to 24 volt, or if you're using, well, let's say 2 6-volt batteries, we connect the positive to the negative, and then we have our 4 volt. If we want to increase the capacity of a battery, but stay at the same voltage, we can parallel the batteries. So we simply connect the 2 positive leads of the batteries together and the 2 negative leads together, and then we grab our power from each end. And the same if we want to increase both voltage and capacity, then we can combine these two to a series parallel connection. It's always good to remember this formula down here. Watts is amp hours times volts, because we are on many boats operating on different voltages. It can be AC loads and DC loads, and to understand those better, it's easier to work in watts, because that's the true power nomination regardless of the voltage, because the voltage and the amp hours are correlating to each other. Low voltage, high amps, generally high voltage, low amp hours. So converting it to watts is going to help you if you're designing or looking at your system. One of the biggest issues potentially with improper wiring is that your batteries could prematurely fail. So it's important to make sure that you're installing them correctly. Try not to install a system like this, where you are grabbing all your loads and charges from battery number 1 and then DC connect the remaining batteries, because what's going to happen is that the front battery is going to be overworked and is also going to be the one that takes the most charge, and the last battery will be the unit that's undercharged. And this is a very expensive experience, because you are going to have to replace your batteries, probably the entire battery bank, pretty early on. So to make sure that we are having a proper installation, we want to have the current flow through all batteries equally. There's two most common ways to do this, is to either use a bus bar and connect the batteries all to the same bus bar. If we're doing this, it's important to have the same cable length here to this bus bar, and then we grab our cabling symmetrical if we're doing this. The most common way is to parallel your batteries and then grab the positive from battery number 1, for example, and your negative from battery number 4. So if you're installing like this, just make sure that the in and out of the batteries are on opposite batteries in the system. So a couple of common questions that we're going to try to cover to the best of our ability and within this 45 minutes. It's going to be what battery bank or what size of battery do I need to power my loads? So trying to give you some tools on how to calculate the size of the battery to maximize your investment. Buying too small of a battery is very expensive, because you're going to have to replace it. Too big of a battery hardly is cost effective. What size inverter do you need? We're going to look at some of the calculations to determine this as well. Solar array and MPPTs, charge regulators if you're choosing to have solar on your boat, as well as chargers. How big of a charger can I use depending on what kind of battery I have, and well, how fast I can possibly charge my system. We're also going to take a quick look at what we should spend extra time and money on. Certain products can be more important depending on the system, and what is not easily added on to increase versus having to replace them if you're investing in too small of a unit. Let's say an inverter, you have to replace that one. You'd have to buy a new, bigger inverter. So we're going to cover that as well as lithium and some of the advantages and how we would go about changing to lithium or installing a lithium bank and what to look for there. So there's 4 general steps to designing a whole electrical system from scratch to finish, whether it's adding on products or if it's starting from the bottom up. The first step is to start designing your system. This is when you would bring out your napkin and start putting down the components that you are looking to integrate. We're not getting into any sizes at this point. We're just trying to get a general overview of the system. So here's where we list an inverter, a charger. We know we want to put some solar up because we want to be a little self-reliant on power. We know we're going to have a generator that we can incorporate, an alternator, can have a battery, so on and so forth. Try to draw that out on a napkin, try to get a general overview of what you think the system is going to look like. This is going to be very helpful for you to collect your thoughts and know where to start. Once we've decided on what we're looking for the system, then we get into the calculations, and this is the time-consuming aspect of it. So that part, we're looking at the power requirements, what kind of equipment we need to use, sizes, fuses, for how long, and so forth. So we're going to dive into those aspects a little bit more in detail as we move along here. The installation aspect is also going to be covered here. What to do, how to look a little bit about different things. And the last thing, which is very important and surprisingly overlooked, is the commissioning of a system. We want to put the system to a test as soon as we've installed it to make sure that if we're missing something, we should be able to fix it early on before something happens out in the water. Design aspect, there's a couple of different things to consider. If it's a new or a existing system is one of them, but also what kind of budgets that the budget fits are sizing the most important aspects of the system. How often will the system be used? This is something that we use seasonal or year round or only for a short period of time. The power consumption is something we're going to cover in depth here, and then also monitoring if that's required or needed. As I said, a quality battery monitor would be the first thing to look into here. So this is basically what a system would look like. We'd have an inverter charger, a battery, we have AC and DC loads and AC and DC charging sources and some monitoring. So let's take a look at those. The first thing, if you are going to use an inverter, is to take a look at the inverter. This is the first thing that you would size in a system. A lot of products will follow the size of the inverter. There's two different styles of inverter. One is a standalone inverter. It converts DC battery power into AC, 120 or 240, 230 volts to run your AC appliances. There's also an charger inverter option, and this is should always try to consider using an inverter charger because it adds quite a lot of benefits to the system. If you are using an inverter charger, like in the picture down here, you can see that we are connecting this one in between the shore power or generator and our AC load panel. And when we are connected to shore or generator, it will start passing through all that power to the AC load panel. So we're not using any battery power here. And if we have more power available from the shore or the grid, we're not using all that's available there, it will start charging the battery. If we need more power, then our inverters will supply extra power from the inverter and the battery to supplement the grid. So it works, works together. So that is seamless. There's a bidirectional relay that allows the current to either charge or discharge to supply the loads. If you're using just a standard inverter, it will be connected to the battery and supply the AC loads, and then a charger will be connected to shore power and then charge the battery. So if the loads on the battery are greater than the charger, then we could potentially discharge the battery as we're connected to shore power. So that's where it's important to have the right size charger for it as well. So it's always a good practice to try to consider using an inverter charger instead of a charger and an inverter, if at all possible. Inverter and a charger standalone is predominantly for smaller system. So the first thing that we want to do when we're designing a power system for a boat or a vessel is to spend some time on load calculation. This is where you really want to try to dive in deep and get a very accurate estimate on how much power you're using, because this is going to dictate the rest of the system, and it's going to set you up for making the right decisions on the sizes of your products. And yeah, spending extra time of this will hopefully save both money and problems down the road to make the right decisions on the product selections that you're going to use. So list all of these, and again, we want to try to use watts as the common reader here. So that way we can tally up both DC and AC load into the same column, so we can get a total power requirement for the 24-hour period that we're going to look at. Way to do this is to take a look at the appliances, and on the back side or on the side on the sticker, it'll tell you how many watts they're running. So a microwave, for example, 1200 watts in this example. We're estimating this one to run 6 minutes a day. So 1200 watts times 0.1, which is 10% of an hour, gives us 120 watts. So we're going to run this. This is going to consume 120 watts per day. So that's one item that we can list. You do the same with the fridge. That one can be an annual consumption. So then we would have to divide this by 365 days to get that 24-hour rate. And we get, in this example, 764 watts. So then we'll start listing all our loads, and the more accurate we can be, the better we're setting ourselves up to. So it's you should spend some time on this aspect here to make sure that your system is deciding according to your loads. Unless your neighbor who's got a very similar system is using the same appliances, you should do this yourself and maybe not look too much at what other people are using and how it's working for them. So it's, yeah, spend some time on this. Once we've tallied all these information up here, we can take a look at what kind of inverter we need to supply the loads here. Try to use the smallest possible inverter. A smaller inverter is more efficient than a large inverter. A large inverter have bigger transformers, FETs. The circuit board requires more power, so the standby power is a lot higher, and an inverter is most efficient when it's working close to its max continuous output. So putting a very small load on a big inverter is not very efficient. So we'll try to pinpoint the smallest possible inverter for the system that's still able to power all your loads, of course. And this is a way to try to figure out what size peak loads. This can be startups on an inductive or let's say an air conditioner or anything that's got a high startup power. The peak of the inverter needs to be within the consumption here and the power requirements, so we're not overloading the inverter. The second one, and this you can just look at the biggest startup power and then add a little cushion there. And then the second one would be the combination of what you would consider the largest amount of loads that are going to stay continuously. So let's say you want to be able to run your air conditioner, and then you want to be able to turn on a microwave and have all these lights and fridges and everything at the same time. Tally up those loads, and that will determine the size of the inverter. So the continuous loads would be needs to be the same size as the inverter or smaller. So the second thing that we will be looking at after that is the batteries. There's a lot of different batteries that can be used for this application. We have flooded AGM gel, there's carbon foam, there's telecom batteries, there's lithium batteries, different types of lithium batteries. So there's a lot of different options out there. Sometimes it can be hard to pinpoint which one is the best one for your application. So let's try to clarify a little bit about what the batteries are truly doing and what's the difference between them are. The system voltage, most sailboats are 12 volts. If it's a bigger boat, you could have 24 volts. Generally, if you have a lot of loads and high loads, it's more convenient to choose a higher system voltage. If, for example, if you have a 1200 watt load like the microwave and you're running that on a 12 volt battery through an inverter, you're going to consume about 100 amp hours. So you need to have cables that can hold 100 amp hours, and you need to have fuses that holds up to that. If you do the same load on a 24 volt system, then you would have 50 amp going through those cables. So your cables are smaller and your fuses are smaller. So stepping up in voltage can be good, but we also want to make sure that we can work with an alternator and DC loads. So it's a little give and take there. Generally on most sailboat, 12 volt will be good enough, but if you have bigger loads, it would be smart to consider stepping the volts up to 24. Another thing to consider is the space and weight restrictions that you may have. Certain batteries, of course, lithium offers less space and also less weight. So if that's an important factor, well, maybe we should take a look at that. As far as the budget comes into selecting the right battery, buying too small of a battery will cost you more money than what you're saving on the initial purchase of it, because it's too small of a battery will work much harder and therefore fail much earlier, and now you have to spend another round of for batteries. So yeah, try to get the battery to at least a 24-hour rate that we're gonna cover here. So when we're designing a battery, a couple of things that we are looking at. The stand-alone time is a 24-hour time generally. You could increase this if you want to, depending on the application. You can calculate on 36, 48 hours, depending on what's most probable for your system. But generally, 24 hours of supplying powers from the battery without any charges or well, anything coming to the battery to supplement this is a good starting point. So to do this, we are doing basically the same way that we're looking at the AC loads. We'll tally up all our loads, AC and DC, that's going to be connected to the battery when we're inverting, and direct DC loads as well will be taken into consideration for the battery size. So we'll tally them up to a 24-hour rate, just like we did before. And then we'll go ahead and divide that by the system voltage. In this case, we have 1800 watts, and we divide that by 12, which is the battery voltage in this system. So that means that we need 150 amp hours to run this system. Now these are rough numbers. There's no loss in calculations in here and the efficiencies and so on. So it's always good to put a slight cushion on this. If we choose to use a AGM or lead-based battery, generally the max discharge is 50%. So at that point, we need to double the capacity for our battery. So in this case, 300 or larger would be the minimum size battery for this application here. If we use lithium, we can use a lot more. So we would be able to get away with 175 amp hours or closer to the true value here, because we can use a lot more of its power. To consider for the battery is how fast we can charge the battery. If we're looking at lead batteries, flooded AGM, they can vary quite a lot depending on the manufacturer, on how fast we can safely charge these batteries without overheating them. A flooded battery is around 10% of its capacity, so a 100 amp hour battery would like to charge around 10 amps with the charger. An AGM can go up to usually 20 amps for a 100 amp hour battery, but certain high capacity AGMs can go much higher. Lithium can take virtually anything that you give to it. You can charge it in 30 minutes if you wanted to, but recommended is around 30. But we can increase that if needed. So this determines the size of your battery charger. So if you have a flooded battery, it's 900 amp hour bank. We want to charge it at the 10% rate. Well, then our battery charger should be somewhere in the 90 amp range. Always good to take a look at the battery manufacturer's specification for optimal charge current here. Some of the charging sources, we have a solar array and MPPT. We want to add a couple of solar panels to charge our batteries to help offset some of the discharge of. So at that point, we can start taking a look at what kind of panels we can fit. On a sailboat, this is usually dictated by real estate. We might not have a lot of room to put up a lot of solar panels, so sometimes the calculations here are not not needed as much because controller. It does not matter if we put them in parallel or in series as far as the power production, put them all in series, because at that point we are getting the voltage up higher, and when we are increasing the panel voltage, we are starting our solar charge controller earlier. Solar charge controller will need around 5 volts above our battery voltage. If our battery voltage is 12 volts, then we need about 17 volts from the solar panel to start the regulator and start charging our batteries. So there's some shading on one, generally most efficient. If you know what kind of solar panels you're using, without getting into too much details, you can take a look on our website. We have a calculator for this where you can put in the values of your solar panel array, and it will give you a recommendation for the smallest possible regulator for your system. And then you can decide whether that's the right regulator, or if you want to step one size up in case you are considering adding on more panels in the future. So what I should spend a little bit extra money on. Pretty straightforward. If you have a deficit, and again, here's where your battery monitor can be very handy. If it takes you a long time to charge your batteries, let's say we know that this AGM battery can take 20% of its rated capacity. We have a 900 amp hour bank, so we can charge it at 180 amp, but we're only charging it at 100 amp, and we're running a generator to charge the battery for a very long period. It would be smart to spend money on that aspect to decrease the fuel consumption from the generator. Always make sure that you get the right size inverter. If buying a too small of an inverter, generally you need to replace that inverter with a larger inverter. You can't just tag one next to it. There are certain inverters that can work together, but dialing in the size of the inverter from the start is pretty important to save money. If you look at example, these batteries, if the batteries are too small, but you have a battery monitor, in the commissioning, when you're doing the test run, you can see this, especially if you see, we used 80% the first night under normal consumption. You know that your batteries are maybe not, the battery bank is not big enough, and you've only put 1 or 2 cycles on the batteries, so you can quickly at that point invest in 1 or 2 more batteries, do the same test, and see, oh, now we're at 50%. So batteries would be one of those things that may not be the most critical to get right the first time if you are able to do the commissioning. Chargers, you can always add extra chargers as well if you're experiencing very long charge time. So yeah, the main thing is to get the right inverter in there to the beginning, and then size the batteries to be able to hold up to that accordingly. Lithium, spending more and more people are converting over to lithium for, well, the reasons that we're going to talk about right here. If you're considering changing to lithium from lead acid, you want to make sure that you are able to do so with your current system. Lithium is a heavy investment, so we want to try to maximize the life of it, and by doing so, we want to put the right charger, the right inverter, so on and so forth into the system to make everything compliant and well, last as long as possible. We want to put the batteries in as good of an environment as possible. Always recommend to connect with a distributor or a dealer, and try not to always purchase products online at third parties such as Amazon and eBay. distributors and dealers can offer the same price as what's online, and with the benefit that you can get support, technical support, design assistance, and they will work with you. So you try to always go to a local distributor when you're designing a system like this, because they can help you tremendously with everything. The last thing is, if you're doing lithium, is to consider temperature if it's a really cold environment, and we'll get into that as well. So one of the main differences between lithium and lead acid is the loss of capacity when we're discharging a lead acid battery fast. If you look at the graph to the right, a lead acid battery is rated at a 20-hour rate. So that means that if we have a 100 amp hour battery, we can get 100 amps out of that battery if we discharge it with a constant discharge for 20 hours. That's about 5% of its rate there, so it's a 0.05 rating. If we start discharging a lead battery much faster, for example, if we're discharging it in 2 hours, you can see that we're dropping the capacity of that battery drastically. Now, at that point, we only have about 30 to 40% of the original capacity. So this 100 amp hour battery, under these circumstances, is now only worth about 40 amps. Factor in that we only want to use half of its capacity, and that 100 amp hour, 20 amp hours under these loads. So lead batteries are not suited for high discharge rates. Lithium, on the other hand, holds its capacity and voltage really well during discharge. So if we discharge a lithium in 2 hours or 0.5 C, at that point we should have the full capacity of that battery to produce all the power. So we're not losing any power at that point. So if you are discharging your batteries, and here's where you can see if we choose too small of a battery bank, if it's lead acid, especially for our system, that we're going to discharge the batteries very fast, and we're going to run through the cycles of this battery very fast and subsequently replace them quite frequently. So when we're looking at the comparison on useful energy, because we should always consider useful energy and not the rated capacity of a battery. 100 amp hour AGM battery should only try to stay about 50% of it, versus lithium, where you can use almost everything in it. So depending on the discharge rate that we were looking at this slide before, you can almost replace a lithium with half its size to a lead acid battery and still have the same capacity for there. This into a different perspective. If we're discharging a lead battery in 2 hours, we have about 30%, and we only have half of that, the 50%, so 15 amps in that battery, versus a lithium where we have the full capacity. As far as cycle life goes, an AGM battery will cycle at this 50% depth of discharge anywhere between 500 to 1200 cycles, depending on the manufacturer. And a lithium at that same 50% will do around 5,000 cycles. And if you're using about 80% of it, it's around 2,000 to 2,500 cycles. So factor that into the equation when you're making a decision on battery, if the longevity of the lithium battery is worth the initial investment here. Second thing that is critical for lithium batteries is low temperature. A lithium battery cannot be charged below freezing. Inside the battery, there's an anode and a cathode, and there's separators in between there. It's sort of a fence where the electrons needs to travel through. And if we're charging this in a really cold temperature, we could potentially damage the separator and parts of the battery because they're not designed to do so. So if you're using lithium in cold weather, you can make sure that you have some sort of protection from charging at cold temperatures, as well as some sort of heating element would you need it for the battery. There's several ways to do this: blanket, a heating pad, you name it. You can still discharge a lithium battery when it's cold. So once we've looked at all these components here, we can start to puzzle together the system that we are looking to install, and we can start moving into the installation aspect of our system. We've selected that we need this many amp hours of batteries, and we know that we want to use lithium or AGM. We have the right size inverter, right size charger, but based on how fast we can charge them, solar panel, so on. We've made sure we have a quality battery monitor, and then we could add more monitoring would we need it, remote monitoring, fully and so forth. So after this, we can essentially take our little napkin diagram and put it into a full size diagram with the components laid out for them. So let's see what time we have here. Oh, we've got a couple more minutes. Equipment sizing. Temperature for inverter is an important aspect. If the inverter, which can sometimes be placed in an engine room where it can be very hot, loses its power depending on the ambient temperature. So the warmer it is, the less power we can continuously provide. As you see the graph here, we can lose quite a lot of power depending on the temperature. So it's very important to try to allow for as much airflow and just try to keep the inverter in a cool place as possible to not only increase the power or get the rated power out of it, but also to increase the lifespan of that inverter. If they're warmer, then there's electronic components in there. They'll fail earlier than what a room temperature inverter would. Fuses and circuit breakers, and here's another thing that a local distributor can always help you with. A lot of manufacturers will have this sort of little template in the manual of the inverter and all the products that they're selling, where it recommends a DC fuse and the size of the cable. So if this is in place, just follow it and you should be in good shape here. And sometimes there are local codes, ABYC codes, those can be good to also take a look at. When you get a recording of this webinar, if you want to dive more into the nitty-gritty of wiring, we have a book called Wiring Unlimited, and there's a link here that you can click on and you can download the e-version of it, and it goes into depth with what is important with wiring, with fuses, circuit breakers, what to consider, DC ripples, symmetrical wiring, so on and so forth. So that's a very handy book, especially if you're new to wiring and fusing. So then we get to the installation, and one of the most critical aspects of the installation is to make sure that you are crimping and making really good connections everywhere in the system. Everything that we're doing is a resistor. The cable is a resistor. The eyelet is a resisting material. The connection, so on and so forth. So to minimize the impact of this to your inverter, charger, to all your loads, we need to make sure this is as tight and well crimped as possible here. So make sure you spend some extra time on doing this right, because it helps your system live longer. And if you have a bad connection, it can even cause a melt terminal. In worst case, it can melt the batteries and so on. So yeah, and there's a lot more in this Wiring Unlimited book on exactly this topic that goes into detail on all this. Another thing to take a look at is the IP rating of your components. There's 7 knot. It's going to be used where there's water, splashes, small boats. You might want to have a higher IP rating. So make sure that your IP rating is up to the task according to where you're going to place the unit. If you're using something in the engine room, well then a water rating might not be needed. But if you're using the unit outside or outdoors or wherever, it can be very important for the life of the charger or inverter, so on. Cooling, something else we talked about with the extraction fans. Try to keep your units at room temperature at all possible, because every producer, every charger, consumer, inverter, so on, will produce heat when they're working. So try to move that air around to keep them as cool as possible. Will only prolong the life of them, and trying to keep the power output of them as high as possible. And the last thing here is the commissioning. So now we've installed our system, we've designed it, we've done all our calculations, we know what we need, we've put everything in place. And at this point, we want to put the system to test. It's always best to put the system to test before we leave the dock. So start small and start turning on your inverter, start turning on small components, and then start to load your system gradually higher and higher. And in the end, we want it to make a full load where we're driving everything that we can on it. And we're starting the engine, charging from the engine. We're connecting to shore power, make sure everything is charging well. And we'll put the system to a test, so to speak. It's always good to find out if we have a missed wire or something once we're at the dock versus out on the water. But start small and build your way up so that's, you don't have a big load impacting a poor connected terminal or something like that. So work your way up, test it, make sure your wires are nice and cool, and have a general overlook of the system. And once we've done that, we should be pretty much good to go. A lot of things to consider here. Working with the local distributor is, I would say, immensely important. They can offer a lot of or doing a whole new one, or you want to increase just the solar panels, or adding on, so on. If you want help with specifically Victron products, you can see the email that we have down here. We're 4 sales managers in the US. You can drop an email here, and it's monitored daily by all of us, and we can direct you to the closest distributor to help here. We also have a where to buy on our website, where it will locate you and tell you who's close to you, and you can reach out to them as well. And I think that's it for me. Thank you so much for having me, provide a little presentation here. So I was going to see if we have any questions here. I don't know if Barb or Hank, do you have anything that you would want to add here? Okay, we had a question here on adding a newer battery to an older bank. Yeah, this is no, don't do that kind of scenario. A new battery will have fully rated capacity. You're only as strong as your weakest cell. So adding a new battery to an old bank will only degrade the output of much better than the old ones. The old ones can have sulfation inside the plates, especially if we're looking at lead batteries. And then they will drop the overall voltage, causing the number one battery to work a lot harder, and you'll have an imbalance in between them. They'll drop voltage. So overall, it just you should always replace the entire battery bank if you're looking to add more capacity. The time when you can add a new battery to a system is if you've not cycled your batteries heavily. Lead batteries, I'd say maybe 30 to 50 cycles or a month or two. At that point, you should be on the safe side, but generally, you just try to stay away from that. Audio is broken up on my computer. Well, I hope that would be a good amp meter gauge for a wind generator showing input. A shunt-based battery monitor can do this. Anytime you want to read output, I would always recommend to use a shunt-based, like in the initial slides here, because that will read and translate what you're seeing to useful numbers for you. So yeah, shunt-based battery monitor can be used to monitor just the wind. Alternatively, you can have it as your main battery monitor, and it will monitor the net effect of all charges and loads and show you what's going on with the battery. Do we have any more questions here? I don't see any more questions. Barb, Hank, do you see any more questions here?
Hi, Simon. No, that was great information. Thank you so much for presenting today. We can wait just a minute here to see if anyone else has a question. Otherwise, you're just getting some thank yous.
Yeah, I hope this sound was okay here. My internet connection here is not very stable, and if it had a couple of hiccups, apologize. If you have any more questions, the email down will try to assist you. But hopefully this is a good tool to give you an indication on where to start when you're looking at adding new products or increasing capacity or whatever you're doing on your power electronic side on your boat. I think you're muted, Hank.
Okay, there we go.
There you go.
Yeah, Simon, thank you very much for this. It was a great help. I might also make a little pitch for our online auction. The Salty Dog Treasure Chest has some items that Simon and Victron have graciously donated to us. An excellent inverter charger, and so you know, you might want to get into that auction and take a look at that. Also a battery monitor, and then also a small-sized charger. So you know, you can get some great deals on those. Someone's going to walk away with some really nice equipment there. And thank you, Simon, for donating that. Let's see. I guess thank you everyone for connecting. I'm going to turn it over to Barb to close things up.
All right.
Thank you so much.
Once again, thank you, Simon, and thank you for everyone for attending. I just wanted to announce that tomorrow we do have a free webinar for those of you heading to Antigua this year. We have arrival update for Antigua-bound dogs, what to expect, with Bob Osborne, the Salty Dog Antigua port officer. So hope you'll all join us for that. And with that, I guess I'll say have a good evening, everyone.
All right. Thanks, Barb. See you, Simon.
Thank you.
Simon.
Take care, everyone.